Now let's have a look at some function tables. So the way to generate a function table is to use ftgen. So we have the ftgen opcode that returns the number of the function table, or an ID for the function table. The first argument to ftgen is the function table number, or if you put 0, it generates a number for you, so we can use 0 there. Second argument is going to be the time of generation, which is always immediately 0, unless you want to defer it, but normally you don't. And then the size of the function table, which can be any size in CSound 7. In CSound 6, you have the limitation of power of 2 sizes for certain types of oscillators and opcodes. It's quite good to, it's generally good to, if you're using, creating like a standard function table, to set a size that is a power of 2, because if you run it with certain oscillators, it can be quite a bit more efficient in the way they access this. So, for instance, I can say a table of 16384 points. Okay. Now, the next argument is going to be the gen that you're going to be invoking to generate the function table. In this case, let's start with a very simple one. It's gen 10, so that basically produces one cycle of waveform based on the addition of harmonics, for which you're going to pass on the weights or the amplitudes of each. So say if you want just a sine wave, you're going to have one harmonic with amplitude 1. If you want to add other harmonic, you can add it with any other amplitudes you want. So let's do something like this, where we have 5 harmonics, and the amplitudes are the reciprocal of the harmonic number. So you can see you just basically add a series of harmonic amplitudes here, and that will generate as many harmonics as you pass on there. Now the next thing that, so when we generate that, the next thing you have to use it, because the function tables are there basically, it's an array of numbers storing a function of some kind. In this case, it's basically a waveform, one cycle of a waveform. So let's use an oscillator to take in that waveform. So the last parameter of the third parameter of the oscillator can be given as the function table that you want to read from. So here you're reading the function table that you stored here in GIFN, and then I'll just use an envelope to smooth the signal. So to create an envelope over the signal with, say, 100 milliseconds of attack, duration P3, and 100 milliseconds of decay. Just a very simple envelope here, linear envelope for this. And now I'm going to send it to the output, and that's our instrument. Really simple one. Now, when we schedule this, and I'm going to schedule it for 5 seconds. Pass on half 0.5, and then say 300 hertz. And now I'm going to put in a scope here, so you can see the waveform in the scope. Okay, so here is the scope that's going to be playing the output, and I'm going to run it. So you can see it's a bit like a sawtooth wave, which you expect with that type of harmonic. It's a severely bandlimited sawtooth wave because it only has 5 harmonics. The more harmonics that you add, the closer it will start getting to an ideal sawtooth wave. And of course, you have to remember that the frequencies in the signal will be 9 times, in this case 9 harmonics, or 10 times you have here the 10th harmonic, the fundamental frequencies. So it's going to go, the signal will have frequencies start at 300 hertz and go all the way to 3000 hertz. So now when you play it, it's brighter and it's a little bit more like a sawtooth wave you expect to be. So that's basically one use of a function table. You can use function tables to do other things. For instance, you might want to store a few numbers in the function table to do something like, so an arpeggiator, for instance. So I'm going to use ftgen again. I'm going to let it generate the number, and I'll put 8 numbers in it, and I'm going to have gen2. Now, what gen2 does is basically copy the values that we have here to the function table. So I'm going to say let's say I'm going to have 0 0.5, 0 0.8, 0 0.25, 0 0.2, 0.5, 0. So you can see here, I got a 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 numbers, something like that. Okay. So these numbers are going to be stored in the function table, and I'm going to add them, add 1 to them. So I'm going to basically pick up an oscillator. Let's use a control signal, K1. I'm going to use an oscill instead of an oscilli, and I will show you why in a minute. I'm going to basically have an amplitude of 1, and I'm going to have a frequency of, say, 0.2 hertz, very slow, and I'm going to read the GFI in 2. Now, I'm going to add P5, add 1 to this. So that's all numbers are going to be like 1 to 1.8, and I'm going to multiply the frequency by that. Okay, so now what we should hear is a series of different pitches, and running at 0.2 hertz. I'm gonna make it last for 20 seconds, so we have a longer thing. So let's see what happens. Okay, so you can see that what we have is basically this oscillator is reading those function table numbers. You're adding 1 to it, and you're multiplying P5 to it, so you're getting different pitches. Now, the reason why I'm using oscill instead of oscilli is because this then becomes a truncating oscillator, which means that when you move from one position to the other in the table, you hold it until you get to the next index, instead of sliding from one to the other. You're not interpolating between the different values. If you use an oscilli, for instance, you'll be interpolating between the different values. And the result is going to be a series of slides, so let's see. Because as the oscillator is reading from that table, it's basically sliding from one number to another. Okay, so that's a good thing. Now, it would be better if we could set these to be like maybe in semitones, and then we could then decide, that these numbers then are basically semitones and so that you can maybe create an arpeggio based on standard scale. So let's say translate this into semitones, and we're going to go from, say, let's say I'm going to create a little arpeggio here, 3, which is a minor third, 4 is major third, 7 semitones is a fifth, 9 semitones a major 6, 10 semitones minor 7, 9, and then back to 7. How many numbers we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have, I think we have all the numbers here now that we need. The thing about this is that this function that we're going to be putting here goes 2, 3, 4, 7, 9, 10, 7, 0 is going to be put on a table, and the table will normalize it between 0 and 1. We can actually guarantee that these numbers are going to be not normalized by giving a negative gen number. So that is basically a code to say don't normalize this function, these numbers, keep them as they are. So then if we multiply by 1, so your amplitude, there you go. Now it's better. Actually, we only have 7 numbers because I counted 2 as part of the number. So that's C. So let's say we have 7, 7 again, and then let's see. So the next thing I want to say now is that we can use also, as this code shows, a function table to hold a whole sound from a sound file, and that's done by using gen1. If you set the function table size to 0 and use gen1, then you can load the whole sound on the function table. These parameters are always 0. They're to do the format of the sound file, but the format of the sound file is always taken from the actual sound file, so we don't need to worry about these 2 parameters. And the fourth parameter there is the channel that you want to read on to the table. In this case, I'm going to read channel 1, but it's a mono file anyway, so it will read from channel 1. So if you reference that function table onto an oscillator, then you can read it from and play back at various pitches. So how do we set the frequency for it? Now think about that. What you want to do is that you want to have the whole sound play back at a certain speed. Okay. So the original speed will be going from the beginning of the file to the end of the file in the duration of the file. Okay, so if we want to set the frequency to play back, that's going to be the reciprocal of that duration. Because if you think about it, what the frequency is basically is the reciprocal of a period. The period in this case being the duration of the file. How can we find the duration of the file? There are 2 ways you can do it. One is to get the length of the function table by using ftlen, and get and divide by the sampling rate of the function table. In this case, because it's you read the samples from a file, then the sampling rate is going to be the sampling rate of the original recording of that file. So if you do that, you're going to get the duration in seconds. Now, if you use that as your whole duration, then all you need to do is basically scale that by whatever pitch you want to then. So if you say you want to play at the original pitch, this P4 will be 1. But if you want to play any other pitch, it will be basically transposing up and down, like we did with playing a file using Diskin. So if we have a reference, in this case here, the reference for this file is C3, and actually C4 actually in this case. It's basically the same as the PCH notation 90 or the median notation 72. So MIDI note 72. If you get any frequency and divide by that reference, then you'll be able to scale the pitch up and down according to that. So if I play that back, and so on. So basically this is a waveform read from a file and then sent in to the output, basically using Oscilli. Now the only thing to remember here is that works in Csound 7, but it won't work on Csound 6 because in Csound 6 Oscilli can't read any tables that are not power of 2 size, and this is not going to be power of 2 size. It's going to be any other size. It's unlikely that your sound is going to be exactly a power of 2 in terms of samples, in terms of number of samples in it. So in that case, in Csound 6, you should use Posil instead, which allows you to do that. And in Csound 7, you can use any oscillator, any opcode, because they can read any table sizes.